Hello, in this video we'll be going over thermodynamics and the intersections of equilibrium, thermo, and electrochem. Our next topic is thermal transfer, and that involves this equation Q equals mcat, where m is in mass and C stands for specific heat in joules per gram Kelvin or Celsius, and T is either in Kelvin or Celsius. And if Q is positive, that means that the reaction is endothermic and gains heat, whereas if it's negative, it's exothermic since it loses energy, and this applies to the whole mass, like the whole solution heats or cools. And objects can transfer energy. So for example, if two blocks of copper and silver were right next to each other and one was hotter than the hotter one can transfer heat to the colder one, giving up energy. And since there's no loss of energy, the energy change equals 0. And so we can set up the equation of the Q for the copper plus the Q of the silver is equal to 0. And here's an example where we have a 100-gram block of copper that is heated at 93.5 degrees Celsius and has a C of 0.387 joules per gram Kelvin, as well as a block of aluminum that's 42 grams heated at 54.5 degrees Celsius with a C of 0.9 joules per gram Kelvin. And we want to find the final equilibrium temperature, assuming a complete conservation of energy. So once again, we can set up the Q of copper plus Q of aluminum is equal to 0. And from there, we can use the Q equals mc delta T equation. And so we can use grams for this since that's what we're given. So 100 times 0.387 times the final temperature minus 366.5, since that's a temperature in Kelvin, plus 42 times 0.9 times the final temperature minus 327.5 is equal to 0. And this works since the final equilibrium temperature is the final temperature in both of the copper and aluminum. And so the final temperature is equal to 347 Kelvin or 74.2 degrees Celsius. We're next going to talk about phase changes. And so for example, for water, we know that the freezing point is 0 degrees Celsius, the boiling point is 100. And so at this temperature, there occurs a potential energy change where there is no increase in particle velocity. It's just energy used to overcome the bonds. So if we were to graph energy and temperature, and we look at the potential energy change points where the graph is horizontal, we'd use N times delta H to find this energy in kilojoules. But for the non-horizontal parts, we use Q equals mc delta T in joules. And overall, these phase changes take up a large amount of energy, especially in comparison to what it takes to excite the molecules. And we're going to be looking at water that's cooled from 125 degrees Celsius to negative 15 degrees. So as you can see, there are 2 phase changes and 3 temperature changes. And overall, we're going to be getting a negative value since we're losing energy. So we have 2 points where we're going to find N times delta H and 3 where we're going to be finding Q's. We are given that this is for 255 grams of water. And we also need to take into account that there are different delta H's and different C's. So there's a delta H of fusion, a delta H for vaporization, and C's for each of the different states of solid, liquid, and gas. And we can start off by calculating N, which is the 255 divided by 18.016, which comes out to 14.1540 moles. Then we can multiply that by the delta H of vaporization to get negative 576 kilojoules, and that's equal to negative 576,000 joules. And we can also multiply that by the delta H of fusion to get negative 85.3 kilojoules, or negative 85,000 joules. And then we can shift over to looking at the Q's. So for the Q for the gaseous state, we have 255 times 1.841 times the difference between 100 minus 125. And that leaves us with negative 11,200 joules. And for the liquid state, we have 255 minus 4.184 times negative 100, which equals negative 107,000 joules. And finally, for the solid Q, we have 255 times 2.092 times negative 15 minus 0, which is equal to negative 8,000 joules. And so we can sum these up and find that the total energy change is negative 788,000 joules. So as we've previously seen, the delta H of the reaction and Q are not equal even though they're related. Delta H deals with the heat per mole of the reaction and deals with stoichiometry, whereas Q is based on the whole solution because it includes the mass, C, and delta T. So we cannot use the two interchangeably and instead need to convert between them. So for example, let's say that for the reaction NaOH solid to Na plus aqueous plus OH minus aqueous, the delta H of reaction is negative 44.50 kilojoules per mole. And we're looking at 205 grams of water plus 32 grams of NaOH. And we're given that the initial temperature is 25 degrees Celsius and need to find the final temperature. So water itself is not involved in the reaction, and so we want to use the limiting reactant, which is the NaOH. So we can multiply the 32 grams of NaOH by 1 mole of NaOH over 40 grams and multiply that by the delta H of negative 44.5 kilojoules per mole NaOH. So the grams and moles NaOH end up canceling, and so we get negative 35.6 kilojoules. Now, delta H and Q almost take the opposite perspectives in terms of the solution and the reaction, and so we have to negate what we got and change that into joules. And so Q is equal to 35,600 joules. And from there we can just use our Q equals mc delta T equation. So we get that number is equal to 205 plus 32 times 4.184 times the final temperature minus 25. And that gives us the final temperature of 60.9 degrees Celsius, which is reasonable since it's absorbed some energy. But on the other hand, if we are given Q and need to find delta H of the reaction, we can set that up by negating Q and dividing that by 1,000 to get the kilojoules, and then dividing that by the moles. Let's say that we have 50 grams of water and 13 grams of KOH. And we have the reaction KOH solid goes to K plus aqueous plus OH minus aqueous. And we have the initial temperature is 20 degrees Celsius and the final temperature is 70.6 degrees Celsius. And we need to find the delta H of the reaction. So the first step here would be to find the Q, and so that would be equal to 63, which is the sum of the masses of both water and KOH, and multiply that by C of 4.184 times the change in temperature, which is 50.6, giving us 13,300 joules. And so the reaction gave off energy that the solution absorbed. So we know that the delta H must be negative, and so we divide that number by 1,000, giving us negative 13.3 kilojoules. And then we need to divide by the moles of KOH, and so that's 13 times 1 mole over 39.1 plus 16 plus 1.008 grams. And so overall, that gives us negative 57.3 kilojoules per mole of reaction. And next we've got Hess's law, in which we use to find the delta H of a reaction. And this works since delta H is a state function, so only the initial and final state matter, not how it actually occurred. So in this example, we're trying to make the reaction FeO solid plus CO gaseous goes to FeS plus CO2 gaseous. And we are given 3 other reactions that we need to use to make this. So first we have Fe2O3 solid plus 3 CO gaseous goes to 2 FeS plus 3 CO2 gaseous, and that has a delta H of negative 23 kilojoules. Then we have 3 Fe2O3 solid plus CO gaseous goes to 2 Fe3O4 solid plus CO2 gaseous with a delta H of negative 39 kilojoules. And lastly, we have Fe3O4 solid plus CO gaseous goes to 3 FeO solid plus CO2 gaseous that has a delta H of positive 18 kilojoules. And what we need to do is manipulate the 3 reactions that we have known delta H's for in order to reach the reaction that we're looking for, and we need to cancel out any extra terms. So starting off, we see that FeO solid is our first reactant, and that's only in the third reaction. And so we need to flip it since it's on the product side, and because it has a coefficient of 3, we need to divide that by 3. And so we have FeO solid plus 1/3 CO2 gaseous goes to 1/3 Fe3O4 solid plus 1/3 CO2 gaseous. And for the delta H, we have to multiply the 18 by negative 1/3. And next we can look for the solid iron on the product side. And so the only one with that is the first reaction, except we need to divide that by 2 since it has a coefficient of 2 when it needs to be 1. So we have 1/2 Fe2O3 solid plus 3/2 CO gaseous goes to FeS plus 3/2 CO2 gaseous, and 1/2 negative 23 kilojoules. Then for the third one, we just take what's left over and use it to make sure that all the extra parts that we have in the sum of our other 2 reactions end up canceling out. So we end up needing to flip the second reaction and divide that by 6. And so we get 1/3 Fe3O4 solid plus 1/6 CO2 gaseous goes to 1/2 Fe2O3 solid plus 1/6 CO2 gaseous. So we end up with negative 1/6 times negative 39 kilojoules. And so when we end up summing everything, the 1/2 Fe2O3 solid and 1/3 Fe3O4 solid end up canceling out entirely, and the CO2 and CO simplify. So we're left with what we want. FeO solid plus CO gaseous goes to CO2 gaseous. And then we can sum each of the delta H's, and so we get negative 11 kilojoules as our final answer. Next, we're revisiting equilibrium, thermochem, and electrochem, and combining them. So I'm going to start off by drawing this galvanic cell with gold and silver, each with a 1 molar concentration and a volume of 3.5 liters. And we are given the reduction potentials for both of them, as well as a change in E of negative 0.0100 volts at 298 Kelvin. And we're asked what's plated out and how much. So by looking at the reduction potentials, we know that gold must be plated out since the number is smaller, and so it's oxidized, and we flip it and inverse the voltage. And so we can write out that the reaction is Au plus 3 Ag goes to Au plus 3 Ag plus, and the standard E will be 0.701 volts. And from there we can use the Nernst equation. So E is equal to E standard minus RT over NF ln Q. So negative 0.01 is equal to negative 8.314 times 298 over 3 times 96485 ln of the quantity 1 plus 3x cubed over 1 minus x. Now, we get these numbers by using the equilibrium concepts that we already know. So for AU plus 3 goes to AU plus 3AG plus. We know that AG and AU are solid, so we discount those. And we have a starting concentration of 1 molar for both of AU and AG. And then based on the coefficients, we subtract x and add 3x. And so we have 1 minus x and 1 plus 3x. Next, we can solve for our unknown variable, and that turns out to be 0.135 molar. And then we can find the moles of gold by multiplying that by the volume. And so we get 0.473 moles of gold. Then we can change that into grams. And so we multiply that by 196.97 grams, giving us 93.2 grams. The next question deals with equilibrium in thermo. So we have 2.11 molars of weak base at 298 Kelvin and a pH of 9.79. And so we're asked for what the delta G standard of 298 is. Our first step is to write out the equilibrium for the weak base, and so we have A minus plus H2O goes to HA plus OH minus. Then we can start to fill out some of the values. So we know that for the first value on the left is 2.11 molars, and the concentrations of HA and OH minus are both 0, so we know that the reaction goes to the right. And next we can use our given pH to find the pOH of 4.21 and then find the OH minus concentration by taking 10 raised to the negative 4.21. And so we end up with 6.17 times 10 to the negative 15. And so we can add that to the product side, subtract that from the reactant side. And so we have 2.11 minus 6.17 times 10 to the negative 5th, and 6.17 times 10 to the negative 5th, and 6.17 times 10 to the negative 5th. So we can calculate our Kb, which is equal to 6.17 times 10 to the negative 5th squared, divided by 2.11 minus 6.17 times 10 to the negative 5th. And so we're left with 1.80 times 10 to the negative 9th, which is reasonable for a weak base. And then we can calculate the delta G standard using negative RT ln K. And so that would be equal to negative 8.314 times 298 times 1.8 times 10 to the negative 9. And so we end up with 49,900 joules per mole, or 49.9 kilojoules per mole, making it a non-spontaneous reaction. In this next example, we have 2A gaseous plus B gaseous goes to 2C gaseous, and we're given that K is equal to 1.69 times 10 to the negative 8 at 95 Kelvin, with a delta H of 34.6 kilojoules per mole, and we're asked to find the temperature of equilibrium. So first we can go ahead and calculate the delta G standard at 95, and so we get negative 8.314 times 95 times ln 1.69 times 10 to the negative 8, so we get 14,100 joules per mole reaction. And from there, we need to calculate the other unknown, which is delta S standard. And so we can plug into delta G standard is equal to delta H standard minus T delta S standard. And so we get 14,100 is equal to 34,600 minus 95 times delta S standard. And so we end up getting a delta S standard of 216 joules per mole Kelvin. And then because it's asking for an equilibrium temperature, we know we're looking at when delta G standard is 0. And so we have 0 is equal to delta H standard minus T delta S standard. And so we are looking at 0 is equal to 34,600 minus T times 216. And so that makes our T of equilibrium equal to 160 Kelvin. Our final problem involves equilibrium and thermo. And so we're given this following table with the delta G standard at 298 Kelvin and the delta H standard and S standard. And we are asked to find the change in the concentration of silver ions. So we can do this using KSP at 298 and KSP of 370. So first we can write out a reaction involving what we're given in the table. So we have Ag2CO3 solid goes to 2Ag plus aqueous plus CO3 aqueous. So now we can calculate the delta G of the reaction, and so that would be 2 times 77.11 minus 527.81 plus 436.8, which is equal to 63.21 kilojoules per mole. We can do the same thing for delta H, so that's 2 times 105.58 minus 677.14 plus 505.8 is equal to 39.82 kilojoules per mole. And we can do the same thing for S, and so that's 2 times 72.68 minus 56.9 minus 167.4, which gives us negative 78.94 joules per mole Kelvin. Then we can go ahead and calculate K at 298, which is equal to E raised to the negative delta G standard over RT, which is equal to E raised to the negative 63,210 divided by 8.314 times 298. And that gives us 8.32 times 10 to the negative 12. Then we can calculate the delta G standard at 370 Kelvin. And so that's equal to 39,820 minus 370 times negative 78.94, which is equal to 69,000. Then we can do the same thing and find that the K at 370 is equal to E raised to the negative 69,000 divided by 8.314 times 370. And that comes out to be 1.81 times 10 to the negative 10. Then using our original reaction, we can write out that K is equal to 2x squared times x, or 4x cubed. And so then we can solve for x at 298 and 370. So at 298, it is 1.28 times 10 to the negative 4, and at 370, it's 3.56 times 10 to the negative 4. And lastly, we can find the Ag plus concentrations at both times. So in both cases, we need to multiply that by 2, since that's the coefficient. And so at 298, that's 2.56 times 10 to the negative 4 molar. And at 370, that is 7.12 times 10 to the negative 4 molar. And the final step is to take the difference between them in order to get the change in Ag plus. And so that would be 4.56 times 10 to the negative 4 molar.
Thank you for listening.